Thank you very much for the invite. It's a great place, Joe, and I've always wanted to speak here. The name of the exhibition just meant, well, I really was very, very keen to do anything I could to support making, which is, as you probably gathered, is a passion of mine, and obviously everybody else is here. And as you heard, I have a kind of strange sort of journey to this point because I started off doing a PhD in jet engine alloys, and now, in fact, one of the things I'm going to talk about is these spoons in front of you, which you're very welcome to kind of have a look at afterwards, which are a set of identical spoons of different materials, so gold, silver, copper, bronze, zinc, chromium, I've missed that one, tin, yeah. And so part of the one thing I want to talk about is how you get to go from designing jet engine alloys to making spoons. Why are those two things at all related? And maybe they're not. No, they are. And I'm going to tell you about them. And so the first thing is I need to kind of set the background, really, and talk about material science, which is, in general, not something most people have come across, which was the reason of working with the BBC to kind of maybe give the subject a bit more visibility. And, of course, materials are, everything is made out of something. So material science seems to be relevant to making, although the exact connection is never usually made very clear. So I just want to talk a bit about that too. And then we'll get back to the spoons and then the Institute of Making. And also I just want to first of all say that a lot of the work I'm going to talk about is not just me. It's a big team of us. And these are some of the people who've been most involved. Especially I want to mention Zoe Laughlin, who's a long-time collaborator, and she's the creative director of the Institute of Making. She's an artist by background, but she did a PhD with me and has kind of gone on to do her own research projects. And Martin Conreen is a designer at Goldsmiths, and he is the making director. Supinia and Philip and Graziella and Harry have all worked on different bits of the research. Okay, so set the scene. Actually, can you see this at all? Anyway, well, I'll just see. This is just a normal picture of an everyday scene in central London. And if you're a material scientist or anyone sort of, I suppose, who kind of cares about materials, then it's quite easy to sort of pick out the different materials in that scene. And the thing is that each one of these is a revolution. Each one of these pushed civilization forward quite a long way. And there are so many of them. And it doesn't even take you very long before you kind of quickly, overwhelmed with identifying different materials, and that is even a tiny proportion of them that you can see there. And of course, getting to grips with each one of these materials is and each person's own. You can easily spend your whole career or your whole life dedicating yourself to expertise in one of these materials and still perhaps only scratch the surface. So materiality in materials is quite an intimidating topic, and just picking out the materials in a scene is itself an intimidating thing. I like to flip it around the other way and say, it's intimidating, but it is glorious, isn't it? I mean, we have made the whole world around us. It's a sort of as sophisticated and as wonderful as an urban jungle. And, we should celebrate these materials because it's no accident that the names of civilizations are named after materials. But what is a material? Actually, at this point, I think I might just throw that question out. Does anyone have a good definition of what a material is? It's a trick question, but anyway, I might as well. Come on. Anyone feel confident? I'll tell you that from a material science perspective, it took me 10 years to realize that there was not one definition in material science of a material that anyone would put their name to. Every material science book you'll ever read, you open the front page, no one will ever define what material is. So we've got a subject based on a word which no one will define. Why? Why is that? That seems odd. This is my take on why it's an impossible thing to define. And it's quite a complicated take. So be patient with me. So the world is a complicated place, and it has different scales. And I've split the world up into two sides, the living world on the left here, and the non-living world on the right. And there's a line down the middle, and I've made different denominations of scale, so 100 meters, 1,000 millimeters, 10 millimeters. It gets smaller and smaller logarithmically as you go down. Now, on the left, people are kind of familiar with the scales I'm talking about because you get to 100 meters is the biggest tree on the planet, roughly, Californian redwoods. Whales are the next kind of biggest category, certainly the biggest category of animal. Then if you zoom in further, you get things like mice. And if you zoom into those, you get the fleas on them. And you zoom into those, you get the hairs on the fleas. And if you zoom into those, it turns out these funny little things down here, it's just my illustration of what a tissue is. So we're multicellular. We're all made of cells, and all the bits of us, our skin, our brain, our hair, our livers, our kidneys, all multicellular. And so that means that the ultimate building block is a cell, and I've got some red blood cells there illustrated. And they're kind of between, they're small. They're microscopic, in fact, which we'll get back to. And they build the whole, you, me, that plant out there, we all started from one cell. So that's how nature builds its stuff. It makes everything from a single cell. And cells themselves have been around for, people debate how long, maybe 4 billion years. And they are very, very complex things. We, in fact, from the scientific perspective, we really don't understand very much about an individual cell. We know some very basic things. We know that they are basically full of molecular machines. And I mean machines in the real sense of the word. They can rotate things. Things travel along them like a little conveyor belt. When you see these things under the microscope, your brain pops because you never really thought that actually this kind of microscopic world, which some animator might have come up with, could be real. And as I say, we don't really understand how they all work and how they interact. And they are where chemistry meets mechanics. Okay, so we don't really know much about that, but what we do know about is inside the cells, there's something called the nucleus, and inside that is DNA, and we know every single bit of DNA. Weirdly enough, we know loads about that, and there's just 4 different types of amino acid, and we've coded them all. So, in fact, it's got so good now that any one of you can give a blood sample, and within a day, we can know your exact genome. That's pretty strange. We don't really know what to do with that information, but anyway, we thought it was going to open up an enormous number of things because it turns out humans only have about 30,000 genes. That's not to say that there's only 30,000 bits of information that make you up or me up. But it is only 30,000 things you can play with. Deconvoluting what that complexity means is something that's difficult. But that's not what I want to talk about. What I want to talk about is how amazing natural materials are and how nature makes things. And the key is, I think, which is where we're going to get to the definition of material, we'll get there in the end, is that nature does this thing where it changes something down here in one of your genes, and actually it doesn't magically change your eye colour just because you change one gene. It doesn't magically give you cancer. What happens is that it changes every single thing along the way. So information travels through dimensions inside your body, affecting everything, affecting the molecular machinery, then the cells, how they change, how they organize their cell, and then the hairs and all these sort of things. You lose your hair using, with chemotherapy for those reasons. And the other thing that happens is that information travels down. So suddenly, if you're a mouse or you or me, and we find ourselves in a desert or a very hot day, actually it's turning genes on in our cells. It's changing the way that we operate. So there's information going up and down. Okay, so then the big question is, what is life? That's for another day. Okay, let's not. We don't even know what a material is. It's easy. I know, I can hear what you're saying. All right. So, materials is on the other side, the inanimate world. We've done quite a good job. We can make really cool things like computers, and I would argue amazing things like spoons, microphones, tables, wonderful concrete that we're all sitting on, this transparent glass. We can do some amazing things. There is all the same scales are in these things. And in fact, it's our manipulation of those scales, at the different scales, that has allowed us to sort of go some way towards equaling nature in its brilliance in creating materials. But it's quite obvious that, you can't really call, in the same way that you can't really call a cell a material, you can sort of maybe call hair a material. But as soon as you refer to anything as a material, you have to work out what it's made of, and also what's above it in the scale as well. So everything essentially becomes a structure. And the structures are just defined at different scales. So on the inanimate side, you have big buildings, obviously. You have smaller robots. They can be, by the way. It's quite exciting. Phones, and then little bits of wire inside the phones, and then these kind of tiny little micro machines, which are about the size of the width of a hair of a flea. So we're making little machines which are that small, which do things. So in fact, that thing where you turn your phone and I know it's a trivial thing, but it's kind of cool. You know, you play around it for ages. That's a little machine called a MEMS machine. It's about the width of a human hair. And if you zoom in today, you find that these things are called crystals. So this, I was going to say this aluminium, this actually, it's polyvinyl chloride probably. But anyway, most things, this concrete is made of crystals, that aluminium surround is made of crystals. So, and that's what they look like under the microscope. And so when I was doing my PhD in jet engines, it turns out that these crystals grow or they shrink at high temperatures inside engines. And when they do that, they change the strength of the material. And that's a bad thing. So what you really basically want to do is try and control the crystal growth inside an engine. That's what we were doing. But if you can change them other times, you can make them do all sorts of things. So my current research is trying to work out how to get metals to heal themselves in the same way that natural materials heal themselves. And it doesn't seem impossible, right? You and I, we cut ourselves, the skin heals back. There's quite a lot of good examples of natural materials that have the machinery to heal themselves. And it's just about, well, we say it's just about, but we've worked out mechanisms, right? So about how some self-healing works over here, and now we're trying to apply it over here. So I guess the key thing I was trying to say is that metals aren't this monolithic thing. You know, you don't have a slab of wood or a slab of concrete or a slab of aluminium. Aluminium is this beautiful structure that goes all the way down, just like you're a beautiful structure. And if you can control the different bits, this area down here is called nanoscale, and people are very excited about nanoscale things because it's very tiny. It's about the scale of the inside of a cell. So all that molecular machinery stuff I was talking to you about is that scale, and it does strange things at scale, the atoms. So they self-assemble. So this tube, for instance, is all a regular, beautiful shape, but no one put all the atoms in place. No one told where the atoms had to go. They just went there. And it's an inanimate material, so it's a bit like putting all your cutlery in a drawer and shutting the drawer and opening up again and find them all neatly stacked. That's what happens at nanoscale. Which is why a lot of people think it might be the key to life, because there's lots of stuff that's kind of crazy. But it also means that it sort of hints at the possibility that self-organisation and self-healing may not be an impossible dream for the inanimate world. Okay, so I've probably talked too long about structure, but this is essentially the problem of how to define a material. For us, wood is a material. For an ant, it's building. For a giant, this building might just be a pebble. So materiality, it all depends on your scale. And all the different scales talk to each other. Okay, hello. Just to complicate things slightly further, I want to tell you a story about one material. And I could have picked any, but I'm going to pick glass, because I think it's quite an amazing story how glass came to be, and how much of it we have around us now. But anyway, material scientists would say that they invented glass, although it's not really true. And they would give you the scale analysis. It was what we do, really, material scientists, is that we kind of immediately draw lines and scales, and then we identify structures inside the glass. So even though glass is invisible, transparent, and it seems to have no structure, of course that is just an illusion. There's loads of atoms in there, and the fact that light travels straight through them is kind of amazing. And we can control that. So you can turn the transparency on and off. In fact, you can even control it with an electric current. So you've probably all seen these electrochromic windows that you turn a current on and the whole thing goes opaque. In fact, some terrible toilets have them in them. And my advice to you is not to go in those. But things like colour is also controlled at the molecular scale. But if you want to control the strength of glass, it isn't molecular defects that you'll care about. There's actually much bigger ones. tiny bubbles are what control the strength of this glass. And it was only until the 20th century that we learned how to get these tiny bubbles in glass down to the point where you could make these enormous sheets of it. And that's why, I mean, if we'd been able to do that earlier, architecture would be different. But only the late 20th century that we could do it cheap enough to have enormous, strong glass. And so you see what we do with it. Photochromic. Has anyone here got a pair of those glasses that change in the light and they go tinted? Photochromic glasses? They're called transition lenses in the part. No. I used to have a pair. Anyway, they're not cool. It really tells me I got rid of them. But they are amazing. So what they are, photographic paper works by putting silver halide, which is a chemical, onto a piece of paper. And when light hits it, it turns it into metal silver. And the transition glasses work exactly the same way, but silver halides are inside the glass. And these are pictures of a little silver halide, little silver crystal grow in real time inside your glass. And they make it dark. And that's how they get dark. And then when you go inside, they're no longer receiving light, so they dissolve back in. So you get a crystal dissolving into an amorphous solid in real time, and you just wear them. And they're still not cool. That's really unfair. Anyway, so there's loads of really good science inside a piece of glass, but that isn't where glass came from. Glass has a much more complicated history. It's not about us sitting down, scratching our heads and thinking, oh, we want a transparent solid. The earliest sort of samples we have of glass this is a pectoral from Tutankhamun's tomb, and that thing in the middle there is not a ruby or an emerald, but it's a piece of desert glass. It turns out that in Libya, there's kind of a bit of sand, a desert in fact, which is almost pure quartz. And when lightning hits that, or very high energy meteorites, it melts it into glass. And to get that clarity of glass, you needed to have a temperatures that the Egyptians couldn't make. They didn't have furnaces hot enough. So we know that is a naturally made bit of glass from the desert, called desert glass. And it's approximately 26 million years old. And the funny thing about glass is that not all cultures took it up as a kind of project, as a material, it was a very interesting juxtaposition between the East and the West. So although the East, so the Egyptians and then the Greeks and then the Romans, big time, took glass up as a material and finally got it to work, it was quite hard to get glass to work because you have to get the right composition, and you have to get it very hot, and then it's sort of gooey, and it's difficult. Well, you probably know. In the East, the Chinese they knew how to make solid glass objects, but they didn't make them. They used glazes a lot. In fact, they were the masters of glazes. And these are two micrographs of two pots, one from the 11th century and one from the 12th century. And I just want to show you these because they were so good at glazing, they could control the bubble size. It's the same bubbles I was talking about that make glass weak, but they also give this real opalescence to the glaze. So they were controlling the bubble size in the glaze of this porcelain bowl. So it wasn't like they were unsophisticated. They knew about glass, but they just didn't make whole objects out of them. And this is a crystallization effect inside this what's called oil spot pottery. And again, they really understood, the Chinese, about growing tiny little defects in order to get optical effects or mechanical effects. So they were easily sophisticated enough to make glass objects, but they chose not to. Meanwhile, in the West, Romans were learning how to blow glass. They made the first windows. They made the first wine glasses. And in fact, so in the East, all drinks are drunk out of porcelain or opaque things, and in the West, the wine glass suddenly makes wine visible, which is an interesting difference. But it wouldn't have made any difference probably. Either way, it's just maybe it's a cultural norm difference, except for in the West, this mastery of glass suddenly yielded something kind of different, which was a glass lens. And if you shape glass, you can get light to bend, and then you can get it to focus, and then you've got a telescope. So by having a lot of brilliant glass makers, they had amazing, wine glasses and windows in their castles and palaces, but they actually had something better in a way. They had the makings of a telescope. And without that, it's arguable that the scientific revolution and the Renaissance and the Enlightenment that followed it may not have happened, because if you can't resolve disputes about whether the Earth goes around the Sun or the Sun goes around the Earth by actually making accurate measurements, or whether Jupiter has moons, then they're just so much talk, right? But actually Galileo just went, I can see the moons, come and have a look at them, and that was very powerful. The microscope followed, as did an enormous blossoming of the craft of glass, of the art of glass, etching of glass, grinding, enameling of glass. And in fact, this, anyone got any ideas what this might be as a glass object? Very pivotal, actually. It's one of the first glass test tubes. So before this, like, chemistry is done by alchemists, and they're trying to work out how the world works, and they're doing it by mostly looking down into a fire, heating things up into opaque crucibles, going mad because mercury was coming out. They fiddled around a lot with mercury, and suddenly, Joseph Priestley et al. The birth of chemistry happens 17th, 18th century because, well, not because that's too much, but anyway, glass is important because you can start to do reactions. You can see when there's a color change, very delicate. You can work out concentrations. In fact, if you go into a chemistry class now, go into a school, go into a university, the one material you'll see everywhere is glass. It defines the subject chemistry, basically. And of course, it's not in the East. They don't do that. And then, of course, as I was saying before, you get mastery of the defect side. So suddenly work out what it really is that determines the strength of glass, and it's not the molecular strength of the bonds, but it's these defects. And you get the birth of the modern city, without which it's very hard to think about. Other forms of, people start mucking about with other forms of glass. So anybody, I haven't had too much on this. And now I'm insisting, I'm going to point to someone and ask them what kind of glass is in here if someone doesn't come up with the answer. I'm warning you. It's a bit too hot for that kind of thing, isn't it? There is a form of new glass in this slide. And is it too hot? Lady with the fiberglass, brilliant. Correct answer. So people start making fibers of glass, which it seems like an odd thing to do. Jaws is the jaw we all watched as kids. Fiberglass. Fiberglass is coming. And it does. It changes all small boats now made of fiberglass. And because people had fibers in their labs, fiddling around with them, they realized that actually one of the great tenets that people thought was true was not true, which is that light doesn't have to travel in a straight line. Light can go around curves as long as you've got the right sort of glass. And you have the optical fibers born. And that's really where all our telephone conversations go down, all of our internet, all the backbone of all of our information world that we have now goes down glass. Incredible. And then, yes, this is a very exotic form of glass, which is called an aerogel. So this is the lightest solid in the world, although it's just been beaten recently, last week, by an even lighter solid. This is 99.8% air. And it's only 3 times more dense than air itself. But there's a new one that's 2 times more dense than air, which is called carbon aerogel. But anyway, that's another story. So I guess the point I wanted to make was, with the glass story, was that I started off by saying, if in order to understand glass, you have to understand the scale of the different structures within it. But that's just one lens of looking at it. That's sort of my lens. And then there's a historical lens, which I just sort of went through very briefly, and that is very brief. And it's all sorts of interconnections about people's lives, about people's culture, about, in the West, revering it for its aesthetic beauty, just so that they could drink a glass of wine and see what it looked like. It didn't have really, you couldn't have predicted that actually it would give birth to the telescope and the microscope into the modern city. You just couldn't have predicted it, but it did. And so those interwoven structures about materials are really what is, I think, the truth about materials, which is that they're not owned by scientists or artists, or they're not owned by anyone. They're everything, and they're kind of, they really are who we are. They represent a lot of our ideals. I think we kind of use them to kind of mirror ourselves into the outside world. So I'm just drawing this diagram here, but basically, I think materials sit within a whole set of people, including historians and jewelers, architects, artists, physicists and chemists, psychologists and chefs, medics, miners, and so I think that's essentially where the subject deserves to be. And it's taken me a long time to get to that mental place myself, having sort of grown up from a scientific career with a particular, being told that materials are this, and this is how you look at them. And so I'm just sharing with you. You probably know this already. So how to go forward from that? Well, I just wanted to show you one of the things we first did is to, this is a vid, oh no, go back. There's a little video, hopefully. No, okay. I'm going to do something different, but that's going to work. Yeah. So this is an event we did at the V&A when they were launching their new ceramics gallery a few years ago. 2009, was that? And they asked us to bring our materials library along. So we've been growing a materials library as a kind of way of trying to get at this point that materials themselves have objectness. They are important to hold them in your hand, not just to understand them from a theoretical perspective. And that actually, the very holding in your hand is part of who they are, and it's part of the communication between us. So we made different teacups out of different materials and got people to taste the same tea out of the different cups to show, or at least to sort of illustrate that actually even something as mundane as drinking a cup of tea is mediated by materials, and they matter. And also just to show how the wide variety of ceramics in this case. So that was a radioactive ceramic, which was made for thousands of years by the Native Americans. And this is we had nothing to do with that, actually, all that. Yeah, so this is an aluminium, this is an exotic ceramic, which it's such a good conductor of heat that you can cut ice with it with your hand, because it conducts the heat from your hand so fast it melts the ice. So you can cut ice like butter if you just hold this thing. So it's just a piece of ceramic, but it's a single crystal aluminium nitride. Anyway, it's kind of amazing. And bricks, of course, and all these kind of things that are around us, which sometimes get missed out of the I'm a ceramic definition. This is a superconducting ceramic to show that actually ceramics have very interesting electrical and mechanical properties. So this will levitate, yeah, hopefully. There, yeah, and they fell off. And yeah, we had the full periodic table of elements. I'm going to skip ahead actually because you're getting the idea. So we had a materials library which we kept building, and we were using it as a conversation between people. Like I was saying, materials are sitting in the middle, and there are all these people, I feel like, who not own it, but who are interested in the subject. And if you give someone, let's say, a copper spoon, then already it's a sort of totemic object between you. It conveys more than it looks, and also the conversation can go many directions. It can go, why would you make a copper spoon? To, what does it taste like? To, oh, I used to have a silver plate spoon, but now it's worn down to the copper underside and it tastes really weird, and that kind of thing. So these objects, they can help this interface. And we did a few events at the Tate Modern where we brought the materials along to have conversations with the paintings and other artworks. This is one that worked really well. We had this material, which essentially is silly putty, and it's a liquid actually, but it looks like a solid. It behaves roughly like a solid. And we just put it in front of these Francis Bacon's, and we just sort of let people, they weren't allowed to touch the paintings or anything else, but they were allowed to touch our materials. And somehow, people had these kind of conversations around them. And so then we realized something else, which I'm just going to quickly show, which is that if you pick a material and you get everybody who knows something about that material in one place, it's quite an interesting thing to do. So we picked flesh for this thing at the welcome, and we tried just to do all flesh. So these are fruits and meats, and we were like, well, these are flesh, but who knows more about these things? Well, this is the world's, at the time, the UK's champion bodybuilder, and he, of course, knows about flesh. He knows about building his own flesh, and what it takes to be a fleshy person, I suppose. And then we had a butcher and he butchered a whole cow for us, and we got people to actually feel all the different tissues in a cow, because it is, I don't know if you have done it, it is an amazing thing. You realise that you grow all these different materials in your body, and they're totally different from each other. And we also got loads of different knives of different materials, so people could understand actually that the cutting instruments, the materials of the cutting instruments, have evolved at the same time as our taste buds have evolved. So actually there's a direct correspondence between what you like to eat and what materials are available in kitchen shops. That's a ceramic knife, by the way. What else would we do? Oh yeah, so the Wellcome Collection is actually a museum about medicine. I don't know if you've been, but it's a really amazing place. It's free. And it's a collection of objects. And these are lots of amputation. These were used in the ships and hospitals. And we thought, well, we weren't allowed to take them out and get people to understand what it's like to amputate a limb, but we could recreate that process. So we got people in there with primitive saws, and they were able to cut through a limb. Or in fact, we had them doing sort of mild dentistry on things. And here was a thing where we built these boxes, because you weren't allowed any of this material inside the museum. So people could feel the difference between an elastic band, which is an elastomer, an artificial one, and actually your tendons and what they're doing. So again, the relationship between the living and the non-living materials. There's a Gunther Hagen's piece there, which is a sliver of a person. And we got people to eat prosciutto next to it. Well, because, partly because but it's the same material, I mean, almost exactly. And yet a completely different context and a completely different way of thinking about the world. And the sculptor from Madame Tussauds, who makes the wax waddles, came along, and she taught people how to make flesh, the artificial version, which is still, wax is still the best material for imitating the kind of waxy, glossy, slightly damp thing that is our skin. And then we got some surgeons in to teach people how to suture. This is pig skin, and you could learn how to suture it exactly the same way that if you have surgery, you will be sutured or have been sutured with exactly the same equipment, to feel what it's like to actually put a needle through flesh and sew it up. I think I'm probably going too far. I just suddenly looked at some horror in people's faces. Anyway, I will go on from that. Sorry. Let's look at something like that. Actually, how am I doing for time? Okay, great. This was the time in which we thought what we need to do is start a kind of club where we can not just do these things at museums and places, but actually we can share the library, which was growing, and we can we can start having projects and people together where we're going to push the boundaries of what materials can do, but we're also going to include everybody in that. So we're not going to just let it be for the engineers and scientists and nanotechnologists to do, or for the medics to do, but actually everybody should be allowed to be involved. And for that, we need to bridge this gap between people's different specialities. So everyone has, not everyone, but the sort of people we're trying to attract all have expert knowledge, but they just happen to be in different areas. And actually they're so deep that getting them to talk across, we thought was going to be our big problem. So we started thinking about how to talk across and get people to work together. And one of the first things we did was talk about sound of materials, because it's something, musical instruments obviously usually use it, so people are used to it. And it's something that is very, very easy to illustrate and quite hard to explain. Why that sounds different from that, and that, and that. That shouldn't sound that bright. Anyway, it does. And okay, so you wouldn't be surprised to know there's a material science take on this. It's very well established. This graph represents it. I don't want you to really look at it. I just want to say a few things, which is that that there's two aspects to this ting. One is how high it is, the frequency, quite high, and that is related. In fact, you can prove this to the density of that glass. So how much mass per volume there is. So if I put lead into this, it suddenly, the density is going to go down, and the frequency will go down. Why is that? That sounds weird. Well, it's because actually what sound is a vibration. I'm shaking the atoms, and if I put heavy atoms in there, they shake more slowly because it takes more energy. So light atoms, low density things sound high, and heavy things sound low. And it's not just that. It's that the atoms are held together by this thing called atomic bonds, and they're the things that allow them to vibrate. They're like springs between the atoms. And if you make the springs very soft, then that means the atoms can easily vibrate. And if you make them very stiff, they can't vibrate very much. So the stiffness of the material, which is that bond strength, over the density is what decides this. So if I change the stiffness of these bonds, which is very hard to do in glass, but it's actually really easy in wood, then I can change the sound of the material. Great. That means potentially that, so one of the things we then did is went on to break glass with sound and work out exactly. So all you have to do is fire the resonant frequency, that frequency, at this object, and it will start really vibrating, just like your dashboard does when you hit 63 miles an hour, that kind of thing. That's a resonance effect. This is a resonance effect. So I get this to vibrate, and then one of the tiny bubbles, which we haven't managed to get rid of, will nucleate a crack, and the whole thing will shatter. And that works. And we tried it out, and we decided, well, where could you go with that? And we thought, well, could you design a set of wine glasses which are only tuned to the owner's voice? So, and when they were angry. So if they rose their voice, all the glasses would start to slightly vibrate. And then if they got really angry, they would all shatter. I think we can do this. But we haven't yet. But that's to give you the flavour of the kind of projects we thought would be nice to do. But you see, in order to do that, we need to get the scientists involved with the makers, involved with the glass blowers, and try to work out where exactly that project would go. And it will probably go off in a different direction altogether. That's a sort of trivial example, really. But that's the kind of thing we were trying. So it makes sense. So actually, it's nice to plot these graphs because you realise that what you know is true is what the equation says, which is, well, that's the scientist's comfort. And this axis is something called the, sorry, that's the pitch, sorry, and this is the other bit of sound, which is how ringy it is, how long it will ring, and how long that note will sustain itself. And that's really to do with how much this material is going to absorb sound. That's called something called the coefficient of absorption, and it's quite hard to calculate that. So we decided to make a whole set of tuning forks out of different materials because we found that no one had really calculated these things, or measured them before. And we also really sort of revered the object as a way of illustrating the point. So these are walnut, ironwood, spruce, glass, tuning fork, zinc, and they all sound different. And it's really amazing because when we got the computer to work out the frequencies and correlate it with what we thought was going to sound, the graph looked fine. But when we got a whole set of musicians in to test the tuning forks, they had a whole different perspective, almost a different dimension as to what that set of objects meant and did and could do. And I think that really taught us a lesson, which was that sort of the science bit of it was just, just sort of springboard into doing something different. Yeah, we did some high-speed camera work on them. This is just to prove that we understood the physics of it. Yeah, we're going to talk about the spoons. So then we thought, well, we did tuning forks. Why don't we do spoons? Why don't we work out why certain metals taste different from each other? So we made these spoons, as I said. And, so what happens in science is someone says to you, why does something work? The first thing you do, if you don't know the answer, is you look it up on the internet, where almost all the scientific research papers are sort of posted. And I looked up if anyone had done any work on this, and no one had done anything. And so we thought, well, we better try and have an idea why some metals might taste different from each other. So we decided it might be to do with their chemistry and how much they would react with the mouth. but we also thought, well, we can test that, but we'd also like to do a set of tests which is about chefs and people who eat. Like, what if we were to give these to a chef, because they all taste different from each other, and show them the results of our study, and then say to them, why don't you design a meal in which you need a zinc spoon, right? You need a zinc spoon to make that dish complete. That the dish is incomplete without that kind of rather strong tasting zinc. And so here's some example. We did blind taste tests. We advertised for the public. Come into our lab, get blindfold. We fed them things with spoons and without spoons. And then we kind of did what, of course, scientists like to do, which is plot graphs. And discovered that people could really tell the difference between very small differences in the chemical properties of the material. They, for instance, could, with a blind taste test, even though they couldn't see that this was gold, everybody said this was the sweetest material. And copper they got immediately is very bitter and very unpleasant metallic. So on the one hand, we gave these to the chefs, and we gave them our results, and we said, can we come up with a meal that somehow takes these results but kind of takes them in a different direction? And then we went to talk to the medics, because the medics, again, I think it's a good example of how an object can really mediate a conversation, because I showed these to the medics, and they said, oh, yeah, well, people who get breast cancer, often their taste changes in their mouth. And we're like, really? And they're like, yeah, loads of diseases. You get a taste malfunction in your mouth, and it's very sensitive. And so then we came up with this idea, well, what if this is a swatch? You know swatches, obviously, but what if this is a taste swatch, which we can really calibrate really precisely? Then having a meal, it's not just an enjoyable thing, it's actually monitoring your taste and if you're healthy or not. And if you suddenly find that the copper tastes different than it does before, maybe actually you could self-diagnose a certain disease. So we sort of sent those people off in different directions. And I can't remember what I've done here. Oh, yeah. And this, I think this essentially sort of embodies what we're doing at the Institute of Making. So we got together with a Michelin star chef to do the meal, and we invited lots of different chefs to come and taste the food, and food writers, and people like Heston Blumenthal, as you might imagine, came along. And I don't really know what the outcome of that's going to be. I think it might take a few years, but all I'm saying is they all know about it now. They've had a meal with it. I thought the curry prawns with the zinc was the best, but who am I to say? But I'm just saying, in 2 years' time, if you see a set of cutlery in Habitat, or no, they've gone bust, or if you see a TV program with someone with a funny, then just remember. But I think it is an important thing to have done, actually, and it's sort of done lots of things for me, because I'm of course interested in this area down here, which is developing new materials and theories and understanding materials from a structural perspective. And I think, I think what we've shown with this study, because it's all been published in scientific journals now, is that actually a team of people comprising of psychologists and artists, engineers and even writers can actually, it's not that they're better at doing research than some other very focused scientific team. It's just that we are. I think that's one of the things I like about this, is that when you get a group of people around the table who've all got different perspectives on materials, then actually the questions you ask are totally different. And I would like to invite you all at some point to be part of one of these research projects, because we are open for that. We've got money to fund the projects, and we've got an open door. Except the only thing I'd say is that we're slightly overwhelmed at the moment with setting up the physical space. So I just moved to UCL, and recently UCL basically looked at what we'd done and said, we'd like to give you a home for this place, and we'd like to fill it with machines for making. We'd like to put the two and two together, so the library and the idea, plus you should actually be able to make the prototype in the place. And so that is being built at the moment at UCL. And again, there'll be open days which you can all come and visit. And it's a two-story loading bay. It's a very basic place, but the library is going to be floor to ceiling with ladders, so it'll be like a sort of book library, but with materials. And the back end of it is all machines for making, But I mean, it's going to be a limited set, like it's inevitably at the beginning, but we'll evolve it. And I think it's kind of an exciting idea. At the moment, it's quite hard for people to be, well, UCL, because they put all the money into it, they're not feeling that they will kind of want to invite everyone to be members. But I do think the future, that will be possible. But certainly I'd like you all to come and visit the library and see what it's like to be surrounded by materials, which is a great thing to do. So the materials library is at the heart of it. We've got this idea of developing new questions, which we can answer by making objects. And then of course we've got the events and exhibitions and stuff like which essentially we kind of feel is a really good way to find new friends, actually. Because actually a lot of the stuff we ended up making was because people had come to a talk or an exhibition and we recognised each other as experimenters. So yeah, you're hearing about this idea not at the beginning, because we've been doing it for about 8 years, building the library and doing these experiments. But you're hearing about it just as we've kind of synthesized it into a real thing, which I think is an exciting moment. And I feel a bit afraid, actually, because you know what it's like when you've been trying to get something to happen for so long and dreaming about it, and then it's going to suddenly be real, and therefore it may not be as good as you thought it was going to be. Anyway, let's not say that. It'll be great. Yes, I think that's really what I wanted to say, actually. Well, thanks for listening.